All right, so we are now into the true applications of vectors, geometric vectors, as opposed to Cartesian vectors. And Cartesian vectors are vectors that are on an x, y, and scary enough as it is, a z axis. So before we start forces, it's down here at the bottom after we've done all the skills. And I'm going to tell you right away that I am not doing two of the questions. The solutions are here, so you can refer to them later. If you want to try them yourselves, you then have a solution for it. And they are in the note, so they're in the blank note, and they aren't in the note. The solutions, like I said, are there. So let's look at force problems. So here is a force problem. And I, again, really like these. So a Highway 401 traffic sign has a mass of 5 kilograms and is suspended along the roadway by wires that make angles of 37 degrees and 72 degrees to the horizontal. Determine the magnitude. So we're going to need, just so you know, we're going to need those things. Determine the magnitude of each tension force in the two supporting wires. So we're not worried about direction. The direction is kind of given to us. We're only worried about magnitude. So we're looking for a number answer. Okay, so let's start the question. So I am going to make a beam of some sort. And, I don't know why that keeps happening. And you've got a sign, and I'll draw the sign in a second. But you've got a sign, and the sign, wrong way, isn't completely centered. It's got two forces that must be acting in an upward direction. Otherwise, it's going to come crashing down to the earth. And I'll put my sign as a little rectangle right here. Now I'm going to make it big enough that I can write a little bit of information in it. And it doesn't matter which tension is which. It's yours to figure out. You'll have two answers in the end. But it says that I can put 72 degrees in one of the corners, and I can put 37 degrees in one of the other corners. So I'm going to put the 37 degrees here because that looks like a smaller angle to my eye. And I'm going to put the 72 degrees here. And what I'm going to write in this box is that you can't use 5 kilograms. I mean, the sign itself is 5 kilograms, but what you don't know if you haven't taken physics is that you have to multiply this by 9.8 meters per second squared, acceleration due to gravity. And that, only because it's a fairly easy calculation, is 49 newtons. So this is what we're going to have to use in the end, and this is the magnitude of the resultant. Because what's going to happen, and I've kind of put things in a spot that isn't all that fantastic, what's going to happen is there's a force pulling down on this sign that's being offset by these two wires. And I get to call them whatever I feel like. I'm going to call this one my tension 1, and I want to know its magnitude. And I'm going to name this tension 2, and I want to know its magnitude. So notice all the little nitty-gritty things that are necessary. Number one, you have to differentiate between, not like calculus differentiate, but you have to make it very clear which one is your tension 1 and which one is your tension 2. You have to make sure that you call them directed line segments, so they're vectors. And you need to say, we're just talking about the magnitude. So basically, and I haven't gotten into this particular thing yet, yet, but you've got this resultant, which is actually going to be in that direction because it's a combination of these two things. So really this should be red. But the resultant, the name of this thing, is an equilibriant. Where did my pen go? And I don't know if I'm saying that right. I can spell it, I just can't say it. So equilibrant. And an equilibrant is the opposite vector to the resultant. So the resultant is opposite to the equilibrant. So now let's draw ourselves a picture that we can actually work with. It means taking the picture that I already have and making a new one. So I'm going to try to do this in this space right here. If I've done this properly, not what I intended to do. Okay, I'm going to leave it as it is. All right, so again, just like when we were dealing with curve sketching, I think that it would be a really good idea to make sure that you draw your pictures as big as you possibly can. So first thing I'm going to do is I'm going to take this vector right here, and I'm going to clone it because I have that magic ability. That's my tension 1. And I'm going to take this one here, and I'm going to clone it, and that's my tension 2. Sorry, vice versa. And what we have to do is you kind of have to fake the picture a little bit, meaning that you've got to make sure that this one is long enough, because remember, I didn't draw this to scale, but you have to make this one long enough that the tip of this one is over the tail of the original. So you're basically adding vectors together. And then I am going to dig out the arrow again and come out with that. But to make it stand out, I'm going to color it red. So I apologize for my awful picture. Now, I'm going to pause because I want to take this picture away from the words, and I don't want you to watch me struggle for that. So hold on a second. Okay, so I did what I said I was going to do, and I added a little more stuff, meaning that I have my T1 here, which is exactly what I called the one that was angled that way. And my T2 was going up to the right, so I called that my T2, both of them magnitudes and both of them vectors. And then here is my resultant vector of 49 newtons from the sine. So what we have to do is we have to somehow build in the angles. So what I like to do, and I'm going to dig out my asymptote symbol, what I like to do is I like to make horizontal lines through the picture. Now I have to move a couple of them, just so you know. So this isn't a very good corner, but so this has to be going through that corner, this has to be going through that corner, this has to be going through that corner. And basically we're playing a bit of a matching game. So I hope you can see that this is the horizontal and this is T1, and this angle here is the same as this angle here, so that's 72 degrees. And because this is 90, that means that this corner in here is actually 18 degrees. So we've got a corner inside this triangle. Then, I hope you can see, just barely, that here's the horizontal and here's tension 2, and there's a 37 degree difference in there. So I can write 37 degrees in here. Now, I'm going to do that in red. And because of the Z law, I can write 37 degrees in here, and that means this being 90 degrees leaves me with 53 degrees for this corner right here. So grade 9 kicks in. And then you can figure out either by Z-ing a 72 into this corner, or by doing 18 plus 53 minus from 180 in a triangle. This corner is a combination of 72 degrees and 37 degrees. So I'm going to dig out my black pen and I'm going to write that this corner is 109 degrees. So we are looking for this corner and this corner. Now I am going to make one last picture. I'm going to take out the arrows and I'm just going to put in the facts. So we have a straight up and down line. We've got a line that goes in this direction. We've got a line that goes into this direction. We've got a corner inside of 18 degrees, of 53 degrees, and of 109 degrees. And this side right here is 49 newtons. Now, I'm going to get super clever and call this triangle ABC. My therefore statement will take into account the tension 1 and tension 2 in a few minutes. So now I'm just going to do sine law or cosine law. Now I look at this and I think, okay, I've got two opposite pieces of information. That means I have to do the sine law. So I'm going to get that scribble out of there and I'm going to set up for the sine law. So sine big A over little a equals sine big B over little b equals sine big C over little c. So I'm looking for little c, and I'm looking for little a. So I'm looking for both of them. Let me put in any values I know. So big A, corner A is 18 degrees. Little a is unknown. Big B is 109 degrees. Little b is 49 newtons. Big C is 53 degrees. Little c is unknown. So I get to do the sine law twice using this middle thing, so middle ratio. So I'm really happy that the ratio with all the numbers ended up in the center. If not, I probably would have started this a little bit different. And now I'm going to do what I need to find A. So technically, I could do cross multiplying here. I can cross this with this and this with this. So what that gives me is A times sine 109, right in here, equals 49 times sine 18 degrees. But my sine 109 that's in here would need to be divided, so I might as well divide that right away, and I'll deal with the calculator in a second. I'm going to do cross multiplying over here as well, so that cross will give us C times sine 109, and in the other direction, 49 times sine 53 degrees, and I'll have that sine 109 sitting in here, so I might as well divide by it and save myself a line. So now it's calculator time for both of them. So little a and little c. And calculator, make sure that your calculator is on degrees because we are not using radians in this question. So 49 times 18 sine for my calculator divided by 109 sine for my calculator equals at the very end, and I get 16.0 to one decimal place. Then I'm going to redo it, but on the other calculation. So 49 times 53 sine on my calculator divided by 109 sine on my calculator equals 41.4. And then I have to refer back to a couple of the pictures. So I'm going to put this on big screen, hoping that it is big enough, just barely. So my little c was my T1, and my little a was my T2. That's what I needed to check. And once again, magnitude. And I screwed that up. Little a is T2. All right, so now I can do a little therefore statement for this. So you have to be specific. You can't actually talk about T1 and T2 because what if you had them reversed from me? I'm going to try to sneak it in here. So the tension in the wire at, so I'm going to do T1, and T1 is at 72 degrees. 72 degrees is 41.4 newtons. And then, and the tension in the wire at 37 degrees, which I can read right here, it's the other one, is 16.0 newtons. And there we have an answer to this question. All right, my hand's cramping, so I'll be back in a sec with a new problem. All right, next problem. Still forces, not tensions. So two forces of 20 newtons and 30 newtons. So good news, we don't have any necessity to do any extra math. It's already in newtons. Act at the same initial point and at an angle of 60 degrees to each other. So I'm going to draw a line when really I want a directed line segment. I'm going to make this my 20 Newton force, and I'm going to make this my 30, so it's longer. And in between them is 60 degrees. So just so I remember. I'm going to see if I can get away with one picture in this case, because there's a whole lot less going on. We want the resultant force's magnitude, and we want its direction. So you have two choices, so there's actually two answers for this, and it depends on whether you decide to take the 30 Newton force and then add on the 20, or if you are going to take the 20 Newton force and then add on the 30. So what I'm going to do is I am going to take this, I'm going to clone it, because I can, and I'm going to put it here. That way it's tip to tail with the 30 Newton force, and because it's tip to tail with the 30 Newton force, that means that I have created a triangle and the ability to draw a resultant. I'm just going to leave it there. I'm obviously struggling. And I'm going to color it red just because I can. And it also means I need to add a few labels. So this is 20 newtons. This is not the resultant, but the magnitude of the resultant, which would be the answer for that side. And because this is 60 degrees, this is 120 degrees, because way back in grade 9, you learned that every line is also made up of 180 degrees. So I'm going to have to find this, which will be the resultant force's magnitude, and I will have to find this, which is the resultant force's direction. And in this case, it's the direction with respect to the 30 Newton force, as opposed to if I had done it the other way, when it would have been with respect to the 20 Newton force. So just quickly, let's see if I can do this. I can clone that after all. I could have made the triangle like this, in which case this is my theta right here, and that is compared to the 20 Newton force. But we only want to do this question once. So I'm leaving it like that. So now we've got a triangle. If you need to recreate the triangle so you can see clearly that we're only going to use the 30 newtons, the 20 newtons, the 120, and I'm going to figure this out. This is the excited bobblehead doll. So this is the cosine law this time. And I'm going to do it in red just because I'm about to try to find the resultant. So it's the resultant squared equals 30 squared plus 20 squared minus 2 times 30 times 20 times the alternate angle, which is 120 degrees. So I'm going to type all that into the calculator. So 30 squared plus 20 squared minus 2 times 30 times 20 times 120 cos on my calculator, and then equals at the very, very end. Don't hit it in between. And you get that number, which is kind of nice that it isn't made up of some silly decimals. And that is not the resultant. That is the resultant squared, even the magnitude of the resultant squared. So I have to square root, which I'm not going to show you on paper, but I will show you here that I have to take the square root and end up, I'm going to go one decimal place, 43.6. And this is going to be newtons. I'll put it there so I don't have to go looking for it later. So that's half the battle. We just figured out the resultant force's magnitude. We now have to find its direction. And in this case, like I said, with respect to the 30 Newton force. So my suggestion is taking that 43.6 and putting it on the picture so that you can see that we now have alternate pieces of information and the sine law is totally appropriate. So sine 120 degrees over its partner 43.6 equals, and I care about theta, and yes, you can label your triangle the way I did in the tension question if you choose, but sine theta over its partner 20. And then I can do the same kind of thing as I did before, and I can cross multiply. This is a little bit different because when we did the tension question, we were looking for a side, which meant when we typed it all into our calculator, we spat out the answer. In this case, we're not looking for a side, we're looking for an angle. So if I cross multiply this way, I'll have 43.6 times sine theta. And the other way is 20 times sine 120 degrees. And I'll have that 43.6 sitting right here, which I will divide out to save myself a line. Now, when I plug this into the calculator, so when I do 20 times sine 120 divided by 43.6, I get a nasty decimal, and that's because that is sine theta. I want to know what theta is, so I have to do second function sine, and that gives me 23.4 degrees. So then I can write a therefore statement that says the resultant is 43.6 newtons, and it acts at 23.4 degrees to, in my case, because of the way I drew the picture, to the 30 Newton force. So you've got to be a little bit specific, and you've got to relate it to the diagram you chose to do. All right, so I've got, like I said, a whole bunch of problems left. I'm going to do this one, but just remember that here is the max question that I referred to in the beginning. So that is Max and me It's my family dog. He's in doggy heaven right now. That's me on a pine decorated reindeer. And then the other one is a box on a ramp, and you can see that solution by accessing it here, box on a ramp problem. But the question we're going to do is number 3. And there is your technical definition for equilibrant force, which I cannot say properly. So it's the same magnitude as the resultant force. So exactly the same newtons, but acting in the opposite direction. So if a resultant is what happens when you're applying force to move something, then equilibrant force is the force required to prevent the object from moving because it's working in the opposite direction. So this particular question says determine the resultant and equilibrant force given this. Now it doesn't say magnitude and it doesn't say direction, so it's both. So unfortunately, we have to do magnitude and direction because these are both vector quantities. All right, so this picture might look a little complicated because it's got 4 forces. It's got the one going up on an angle, down on an angle, horizontal to the left, horizontal to the right. But these two act in opposition to each other, and these two act in opposition to each other. So what we eventually have to do is we have to combine them. So if you think about it, from here to here is 9 newtons, and from here to here is 3 newtons. So what ends up happening is you end up having, and this is not my final picture, a 6 Newton force acting in that direction because this one offsets part of that. And then you also have one that eventually will be acting to the right, and that will be a 13 Newton force because 2 from 15 is 13. And this corner is 80 degrees. But this present picture is not tip to tail like we had to do here. So we have to make an adjustment. And this is why I said that's not the final picture. So I am going to choose, and it doesn't matter, you have to be specific in your therefore statement. I'm going to choose to lay down my 13 Newton force this way, and then I'm going to add my 6 Newton force this way, and my resultant will be here. So I am going to color my resultant red, like I always have for consistency. And then I'm going to draw you another vector. I'm going to draw one that lies just slightly above or below it, or on it if you really want. And I'm going to color that one blue for kicks. And that one is the equilibrant force. So I'm going to do all my work to find this, knowing that when I find the magnitude of the resultant, the blue thing is exactly the same. I'm going to put some numbers on here. So this is 6 newtons. This is 13 newtons. This was 80 degrees, so that makes this 100. And the reason I say that is because way back in the olden days of grade 9, you had parallel line geometric properties, and this is the C shape with 2 parallel lines. And inside a C shape, this is 80, and this is 180 minus 80, so that's 100. So I'm just going to get that out of here. That's 100, and I am going to, just for fun, I'm going to call this triangle ABC again. And that might make it easier to do the math. And this is another cosine law question, because I've got a side and the angle trapped in between. So I'm going to dig out the red pen and set this up. So now maybe you see why your grade 10 and 11 teachers tried to pound this stuff into your brain. Okay, so remember, no equals till the end. 13, oh shoot. 13 squared plus 6 squared minus 2 times 13 times 6 times, for me it's backwards, equals at the very end, and I get 232, and then I forgot, 232.0891 is what I'm going to write down. And then I have to take that and I have to square root it. I don't have to show it. I have to do it. And I get 15.2. And that will be 15.2 newtons. So to be honest, that's a 2-for-1 deal. We just figured out that the resultant's magnitude is 15.2 newtons and the equilibrant's magnitude is also 15.2 newtons. So that's kind of nice. So now, remembering that the resultant is red and doing all the work for that, I am looking for this corner right here. And now that I have two opposite pieces of information, I can do the sine law. So I'm going to do sine of 100 over 15.2 equals sine of that dot, which is in A, over 6. And this is going to be the second function sine 1 again. So I'll have 6 times sine 100. And I'll have 15.2 sine A over here, so I'll have to divide by 15.2. And eventually I'll spit out A. So 6 times 100, the sine button, divided by 15.2 equals second function sine. I get 22.9 degrees. So you can do exactly the same thing to figure out this corner. You can do sine of 100 degrees over 15.2 equals sine of big C over 13 and do all the work. But to be perfectly honest, I have less energy for that because I have a quick way of doing it. So I've got 180 minus the 100 in this corner minus the 22.9 from the corner we just found. Gives me 57.1 degrees. Notice I did that in blue so I can tell that it's the equilibrant. All right, now for the therefore statements. So remember, this is the end of this note. So the therefore, the resultant is 15.2 newtons acting at 22.9 degrees to the 13 Newton force. So because of the way I drew the picture, sort of like the last one, the resultant is compared to the 13 Newton force because that's the one we started with. I can also say, therefore, the equilibrant is 15.2 newtons, acting at 57.1 degrees, and that 57.1 degrees is compared to the 6 Newton force. And there you have forces. Okay, so like I said, Max and me, box on a ramp, it's a sheet. So don't forget to check out those other problems. If you need a hand, let me know. And I guess it's not on Edsby, it's on the site now. All right. Done.